Hello, now let us solve the problem together. The function f of x equals to x cubed is given, and a point with coordinates x node and y node is an arbitrary point on belonging to r squared. It means that this is a point on the coordinate system. Okay? We want to prove that wherever this point is chosen on the plane, it is always possible to draw a tangent line to the graph of this function that passes through this point as well. Okay, so let me just sketch the graph of this one. Might be that it's a little bit useful. So this is a very famous function. So it has a torus point at the origin. So this is the graph of this function. As let me write it like this: f of x equals to x cubed. And then we want to see that, we want to prove that wherever this point is, it is possible to draw a tangent line to the curve that passes through this point. Of course, if this point is on the curve, the problem is simple, but it should also be mentioned. So let us say that, for example, this point lies here on the curve. Okay, and I want to show that it is possible to draw a tangent line. The reason is clear, because this function is a polynomial function, and polynomial functions are differentiable everywhere. So if I ask you, can you write an equation for that? You would say yes. So you need to differentiate the function first. It becomes 3x squared. And then you need to find the k value of the tangent line that passes through this. But in that case, if this point lies on the curve, this point is the point of tangency. And if you want to calculate the k value, you need to differentiate and replace x with the x coordinate of the point of that tangency. The number that you get is your k value. So that's actually important in this problem. If you want to find the k value for the tangent, you need to differentiate your function, but you have to replace the x value with the x coordinate of the point of tangency only. Okay, in this case, I don't have any problems, so I have to replace x with the x coordinate of the point of tangency. If this point is here, the x coordinate is x node, and then of course this becomes 3x node squared. And if I ask you to write the equation, you would say that y minus y node equals to k value is 3x node squared, and then x minus x node. So here, x node and y node are given, so this is the equation of the line. So that's guaranteed if the point is here. But the problem becomes a little bit more interesting if this point lies somewhere outside the curve. For example, let us consider it here, x node and y node. Okay, so you see that still I can draw a tangent line. Okay, so you still see that I can draw this tangent line. So let us assume that we want to show that no matter where this point is, it is always possible to draw a tangent line to the curve again. But of course, the important point here is that this point is now outside the curve. So that is not the point of tangency, even though it lies on the line. So I cannot calculate the k value as I did before. I can calculate the k value using the derivative, but I need to know the x coordinate of the point of tangency, which I don't know. Okay? So in this problem, you need to think in this way. X node and y node is offered to you, so you know x node and y node, and you are supposed to somehow derive the equation of this line. Okay, so what can I do? I can assume that I can pretend that I know the point of tangency by saying that, okay, let us assume that the x coordinate of the point of tangency is a. But because this point is supposed to lie on the curve, if the x coordinate is a, the y coordinate can be calculated using the function. So this becomes a cubed. And now I will act as before. I will try to find an equation for this orange line here. So what should I do? I need to differentiate, which I already did, and then I replace x with the x coordinate of the point of tangency. Okay, so this k value, the new k value becomes f prime of a, which is 3a squared. And then I write my equation. So this becomes y minus the y coordinate of the point of tangency, a cubed, is equal to the k value, which is 3a squared, minus x minus the x coordinate of the point of tangency. So what I did, this is an equation for this orange line. But I cannot claim that I found it because still I don't know a. A is still missing. Okay, but I have another constraint. This orange line is not only supposed to pass through this point of tangency, but it is also supposed to pass through this given x node and y node. So this means that the coordinates of that point should satisfy this equation. Okay, so I have to replace x and y with the x and y coordinates of this point and solve for a. When I solve it for a, then I will find that a, put it back in this equation, then I have my equation of the tangent line. But let us see how it goes. Here, I replace y with y node, minus a cubed is equal to 3a squared, and then I have, instead of x, I put the x coordinate there, x node minus a. So if I ask you what is unknown here, I want you to understand, just a is unknown. I told you that x node and y node is given to you. And you want to show that it is always possible to draw a tangent line from that given point. So here, I want to solve that one. Okay, so in principle, what I can do, I can write y node minus a cubed. I multiply this in, so this becomes 3x node a squared minus 3a cubed. I move this to the other side because I want to solve this third degree equation. So I move it to the other side. There is a minus a cubed here. So totally it becomes 2a cubed. I move this to the other side. It becomes minus 3x node a squared. And then there is also a y node left there equals to 0. Okay? So in principle, I should solve this third degree equation and find a. Whatever I find for a, I put it back into this equation, then I will get an equation for the tangent line. Depending on how many solutions are there, I will get that number of tangent lines. For example, if there are no solutions for this equation for a given x node and y node, it means that it is not possible to draw a tangent line from that given point x node and y node. If there is one solution to this, it means that there exists one tangent line, I don't know, two solutions, two tangent lines, three solutions, which is at most, because this is third degree polynomial, then I will have three solutions. But the problem claims that you want to show that it is possible to draw a tangent line passing through this. So this means that I want to guarantee that whatever x node and y node are, this equation has at least one solution. Okay? And in this case, what I will do, I want to use the intermediate value theorem. So let me write it for short, intermediate value theorem. How? I define a polynomial, p of a, being this expression. So 2a cubed minus 3x node a squared plus y node. So it's a polynomial. I define this polynomial of a, but I know that the limit of p of a when a goes to positive infinity is positive infinity, because when I send a to positive infinity, only this term will dominate. And when I send a to positive infinity, the answer becomes positive infinity because this is a cubed. And when I send a to negative infinity, what happens here? This becomes negative infinity. Okay, so what does it mean? It means that if I want to sketch the graph, if I say that this is the axis for a and this is the axis for p, the function, I know that at the rightmost, when a is positive infinity, p goes very high, somewhere here. And when a goes to negative infinity, leftmost part, then the function goes to negative infinity. So something like this, for example. Down there and up there. And then the functions should start somewhere there and reaches itself. And goes to up to this point. But this polynomial function is continuous. So no matter how this function goes from here to there, it will definitely cut the x-axis at some point. What does it mean? For example, I don't know the graph. For example, it goes like this, and then I would say that, okay, this point is C. The cut point is C. What does it mean? It means P of C is 0. So this means that this equation has at least one root, and that root is C. Okay? So this means that here I am sure that this equation has at least one root, and that is, for example, in this picture C. I take that C back with me and put it here. Y minus C cubed is equal to 3C squared x minus C. And that would be the equation of that tangent line that passes through that point. So it is confirmed that it is always possible that I find at least one root of this equation, which translates itself to having at least one tangent line passing through that given point. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.